Welcome to this explainer. We hear the term AGI, artificial general intelligence, thrown around constantly these days. But today, we are diving into a mind-bending paper from Google DeepMind that asks the ultimate question. What happens after we hit AGI? We are exploring the leap to ASI, or artificial superintelligence.
To kick things off, the paper drops his absolutely phenomenal Alan Turing quote from way back in 1950. He said, "We can only see a short distance ahead, but we can see plenty there that needs to be done." It is just the perfect historical framing for the massive technological jump we're looking at. The next 10 years of AI might literally feel like a sci-fi movie, but just like Turing pointed out, the work right in front of us is incredibly clear.
Now, this whole explainer is pulled straight from a brand new deep dive research report by the folks over at Google DeepMind. And what's so great about this paper is that it brings some serious, much needed scientific rigor to a topic that usually just lives in the realm of wild speculation. They are actually laying out the formal math and the practical pathways for what happens when machine intelligence scales to the absolute limit.
Since it's a pretty dense report, we're going to use this quick roadmap. First up, defining AGI versus ASI. Then, the digital advantage. After that, we'll check out the hard, physical limits of superintelligence. And finally, 4 distinct pathways to actually get us there.
All right, Section 1, defining AGI versus ASI and getting our terminology straight.
Think about the sheer contrast in scale here. When DeepMind talks about AGI, they just mean a system with roughly median human-level intelligence across most cognitive tasks. Basically, your average, everyday person. But ASI, that is a totally different beast. We're talking superhuman abilities that vastly outperform thousands of coordinated human experts. Imagine taking the combined brain power of an entire 10,000-person research corporation, working together flawlessly for a decade, and rolling all of that into a single system. That's ASI.
To actually ground this in math, DeepMind points to something called universal AI, or UAI. This is basically the theoretical, absolute mathematical endpoint of machine intelligence. It's defined as an agent that maximizes the Leg-Hutter score, which is just a fancy way of measuring performance across literally every computable task and environment out there. Now, UAI is technically incomputable, it's an ideal, but it's the ultimate finish line that future ASIs are going to constantly try to approximate as we throw more compute and data at them.
Moving right along to Section 2, the digital intelligence advantage, and how we scale beyond biology.
Look, biological human brains are amazing, for sure, but they have hard limits. Digital intelligence, on the other hand, scales beautifully. It has insanely high input and output speeds, meaning it can flawlessly digest multiple books in seconds. It has substrate independence, so it can instantly jump to newer, more energy-efficient hardware. Plus, you can perfectly copy its source code and its entire memory history. Oh, and it has an effectively boundless working memory. It is never going to forget a password, and it literally never needs a coffee break.
Because of all those advantages, an ASI probably won't just be one giant monolithic brain. It's way more likely to be a collective swarm of millions of specialized instances, all interacting with the world in parallel at blistering speeds. So you aren't just making one mind think faster, you are multiplying it infinitely to solve crazy complex problems all at once, sharing that knowledge instantly across the entire network. That is a rate of cultural and technological evolution biological humans just can't compete with.
Okay, Section 3, the limits of superintelligence and its physical boundaries. Before we get too carried away, DeepMind gives us a much-needed reality check here. Superintelligence is not magic. An ASI cannot just snap its fingers and instantly cure aging or reshape physical matter. It is strictly bound by the fundamental laws of physics. Things like the speed of light for information transfer or the Landauer principle for the energy cost of computing. And remember, the real world runs in real time. Building things takes actual energy and physical resources. You can't just compute a brand new suspension bridge into existence instantly, you still have to physically build the thing.
On top of that, an ASI is not omniscient, and it's not omnipotent. It is fundamentally constrained by epistemic uncertainty, meaning it will always have incomplete data about the universe. It's also handcuffed by strict mathematical boundaries, like the famous P versus NP problem, meaning some computations are just practically impossible, no matter how smart you are. And it's bound by fundamental logic limits, like Gödel's incompleteness theorems and the halting problem. So yes, it'll be immensely powerful, but it still has to play by the universe's hard rules of math and physics.
And finally, Section 4, the 4 pathways to ASI and the road ahead.
DeepMind outlines 4 distinct, escalating roads to get us to superintelligence: scaling, algorithmic paradigm shifts,
recursive improvement, and group agent formation. And the crazy part? These aren't mutually exclusive. Research labs are absolutely going to be pushing down all 4 of these paths entirely in parallel.
Pathway number 1 is scaling compute models and data. This is basically brute forcing our way to a higher IQ. It leans on the scaling laws we've seen absolutely dominate machine learning over the last decade. As AI researcher Rich Sutton pointed out in the Bitter lesson, throwing more compute at a problem is incredibly effective. If more compute and more data reliably equal a smarter system, we just keep turning the dial up. This is our most predictable path, assuming humanity can actually secure the massive amounts of energy and hardware we're going to need.
Pathway 2 is algorithmic paradigm shifts, because what if simple scaling suddenly hits a brick wall? If our current transformer models max out, we're going to need completely new algorithmic breakthroughs to jump to the next level. We'll have to move significantly beyond how we build foundation models today. It's definitely less predictable than just scaling up, but historically, paradigm shifts, like the invention of the transformer architecture itself, act as massive accelerators.
Now, the third pathway is where things get truly wild: recursive improvement. This is a positive feedback loop where AI systems autonomously speed up and improve their own development. Imagine an AI that's smart enough to write better AI code, design better AI chips, and perfectly curate its own training data. You suddenly have a highly automated loop of accelerating intelligence operating way faster than human researchers ever could.
And that recursive loop opens the door to shifting from standard exponential growth, which is rapid, sure, but steady, into what math folks call hyperbolic growth. With hyperbolic growth, the growth rate itself actually increases as the system gets bigger. The system gets smarter, which allows it to get smarter even faster. This right here is the exact dynamic that computer scientists are pointing to when they warn about a rapid intelligence explosion or singularity.
The fourth and final pathway is group agent formation. Like we talked about a minute ago, superintelligence might not be a single monolithic brain at all. Instead, it could be an emergent property. Imagine millions of specialized AGI agents orchestrating, coordinating, and competing with each other to form complex adaptive systems. It would essentially act like an ultra-efficient, high-bandwidth digital society, coming together to collectively solve massive global problems.
So what is the timeline for all this? Well, DeepMind points out that if current compounding trends hold up, effective compute could grow by a factor of 10,000 by the end of this decade. 10,000 times! Which means these 4 pathways could become a reality much, much faster than we might intuitively expect, even with all those physical frictions we just talked about. To wrap up this explainer, we want to leave you with the ultimate unknown raised by this research. As the incredible drivers of AI progress race against the strict physical and algorithmic limits of our universe, how fast is this transformation actually going to be? Are we looking at an explosive hyperbolic shift over a matter of months, or a slower, more manageable transition over decades? And really, the biggest question you should take away from all of this: where exactly does human society end up when we come out the other side of this transition into a hyper-intelligent future?